you all? Okay. Do you remember what we have discussed in our previous session? Yes? S equals Q by M delta T. S is the specific heat. How did we derive this? Q is proportional to M. That means the amount of heat required is directly proportional to mass. And the amount of heat energy supplied is directly proportional to the change in the temperature. Correct? So from this we have derived this equation where S is the proportionality constant, which is called as specific heat. And we have learned that specific heat depends on the nature of the substance. Correct? And we have learned about the units of specific heat. The CGS units of the specific heat, we have heat here first, so that would be calorie divided by mass is grams, temperature in CGS degrees Celsius. What could that be in SI? Again, SI units of heat is joules. There is a division here, divided by mass. SI unit of mass is kilograms. Wonderful. And temperature is Kelvin. So these are the units of specific heat. Okay. And what else did we discuss about the applications? The most important application of the specific heat we observe in the oceans. The ocean water. What do we call oceans? As the heat storehouses. Why? Because water has a greater specific heat. The specific heat of water is higher. That means water would be able to take a lot of heat energy without showing any substantial change in the temperature. Without showing much change in the temperature, water can take and store heat energy. So that's why we call oceans as heat storehouses. They absorb the heat energy without much change in the temperature, and hence they moderate the temperature of the surroundings. Alright? Okay. Moving on, today we are going to look at how the temperature changes when two or more samples with different temperatures are mixed. So when two or more samples with different temperatures are mixed, let's look at how the resultant temperature is going to be determined. Okay. So before jumping into that, let's look at a situation here. We have two beakers and they are filled with 200 ml of water. So we have 200 ml water in both these beakers. Alright, and the temperature of the water in both the beakers is 60 degrees Celsius. We mix them together and pour the entire mixture in a bigger beaker. So we pour this sample 1 and sample 2 in a bigger beaker. Now my question is, so we know that this would be 400 ml of water. So the question is, what is the temperature of this mixture? What could be the temperature of the mixture? Any answers? Would it be greater than 60 or less than 60 or exactly 60? Alright. Really? Okay. Both are at 60 degrees Celsius. Without any loss of heat, I am just mixing them in a bigger beaker. Let's assume that there is no loss of heat to the surroundings. Heat is not lost to the surroundings. Okay, that's easy. Fine. Yeah, you're right. It would be equal to 60 degrees because both are at 60 60 degrees Celsius only, right? That means they are at thermal equilibrium. Correct? Yes or no? Heat is neither gained nor lost. Whenever they are poured into even a bigger beaker, it's not lost or it's not gained. So temperature would remain the same, 60 degrees Celsius. Okay, now I'm gonna change this. Think of another situation. So now we have 200 ml water here, but this time the temperature of the water in this beaker is 90 degrees Celsius and temperature of water in the second beaker is as it is 60 degrees Celsius. Now these are mixed. Of course it would be 400 ml of water. Now what could be the temperature? Just give me an estimate. If you don't have to give me the exact value, just an estimate. What do you think the temperature could be, or in what range the temperature could be?
Please come again.
Little difficult? Okay. I'll repeat my question. You have 200 ml of water in beaker number A, beaker A, and you have 200 ml of water in beaker B. The temperature of water in beaker A is 90 degrees Celsius.
Okay.
And the temperature of water in beaker B is 60 degrees Celsius.
Okay.
So temperatures are different apparently.
Yes.
You mix them.
Okay.
So we all know it would be 400 ml. I don't have to mention it. But the question is, what could be the temperature of the mixture?
Maybe I think so. Average temperature.
So yes, correct. Somewhere between 60 and 90 average temperature. Wonderful, very good, correct. Now let me change this scenario once again then. Now in beaker A, I have 100 ml of water heated to 90 degrees Celsius. Okay, so beaker A has 100, mass is different now, volume is different now. I mean the quantity of water is different. So in beaker A, I have taken 100 ml of water, and in beaker B, I have taken 200 ml. So the mixture would be of course 300 ml of water. So here in the first case, the temperature is 90 degrees Celsius, and in the second beaker it is 60 degrees Celsius. We mix them.
Okay.
What could be the temperature of the mixture?
60 degrees, I think, because of the quantity of the water is high. But high temperature water level is quantity of the temperature
Is low.
So that's why we can average that. We can there should be maintained a low temperature of the high quantity of the water. Temperature will be maintained there.
Okay, that's a good point, but I'll ask you a question now.
Okay.
You are mixing this 100 ml of water also in the mixture.
Okay.
So this apparently has more heat energy.
Okay.
So where does that go? If you say this could be 60 degrees Celsius.
Okay.
This could be 60 degrees Celsius, but it has some amount of heat which this water should supply, right? It is not nil. It is 100 ml.
Okay.
Then how can that heat energy disappear?
So this situation also can average the temperature.
Okay. So is it exactly average of these two, or could there be any changes, because volume is not same. I mean the quantity of water is not same. So do you think we can arrive at any formula to solve this?
Temperature T is equal to T1 plus T2.
Okay. So that is the sum. T equals T1 plus T2. If I apply that here, I would be getting 150 degrees Celsius, which is not quite the case, is it?
Will you please explain?
Of course. Sure. So the topic that we are going to learn today is principle of method of mixtures. Are you excited to learn about this?
Yes.
Yes. Let's see how this works. So let's take two samples. going to be calling this sample 1, okay, with water, and we'll take sample 2 with some amount of water. So let's say sample 1 is at T1 temperature T1, okay, and this is at temperature T2. So basically the temperatures of these samples are different. Also the mass of the substance or of the liquid here is M1, okay, and this one is of M2. So masses are also different, correct?
Yes.
Yeah, fine. Let's say this is our hotter sample and this is a colder sample. So T1 is greater than T2. I mix these both in a bigger beaker. Now, once I do this, no, what happens once I pour this liquid and also this one here? This is the hotter sample and this is the colder sample. What did we learn about heat? Heat is a form of, yes, go ahead.
Decrease.
Heat is a form of energy which will flow from hotter object to the colder object when in thermal contact, right? Heat flows from hotter body to the colder body, and this flow arises due to the temperature differences. Now here the temperature is different. This is the hotter one and this is the colder one. We are pouring it into a bigger beaker. That means they have come in thermal contact, right? That means heat energy flows now. How does that flow? From hotter to the colder. This is how the heat energy flows. So that means this sample will lose some heat energy and this sample will gain some heat energy. Now whatever the temperature this has, it would be in between T1 and T2, right? Let's say the temperature of the sample is some T. Okay. So T would be less than the T1, less than the hotter sample, correct? And it would be more than T2, more than colder sample, correct? So if it is 90 degrees Celsius and if this is 60 degrees Celsius, then it would be somewhere in between 90 and 60. We don't know exactly what it is. We'll be getting to that in a minute. For now, that's what you do, right? Even when you're taking bath. If the water in your bucket is too hot, what do? You pour some cold water into it.
Yes.
So what is the idea? You want to make it less hotter,
Yes.
but at the same time you don't want it to be very cold, right?
Yes, right.
So that's you balance it between these two temperatures, right? Hot and cold temperatures you want somewhere here. That's why you mix them, no?
Okay.
Yes or no?
Yes.
Yes. Same thing happens here. So this mixture will have a temperature in between T1 and T2. That means less than the hotter one but greater than the colder one. Why? Because heat energy flows from hotter to the colder objects. That's what is happening. Clear up until this point?
Yes.
Okay, cool. Some T. So this is the hotter one and this is the colder one. Fine. Now, when we mix these two, the heat lost by the hotter sample is transferred to the colder sample, correct? That means, can I say heat lost by sample 1 is equal to heat gained by sample 2? Yes or no?
Yes.
Any doubts up until this point?
No.
Okay. Now let's solve for this one. Heat lost by sample 1. Okay. I'm going to be writing this as B1, that is beaker 1. Now you know that we know from the previous session we have studied S is equals to Q by M delta T. Correct? From this Q equal to delta T. Yeah. So now the liquid present in both these beakers, let's say they are of the same substance, water. Okay. So now heat lost by sample 1, Q1 is equals to S, mass is M1. Now, yeah, this is not temperature. This is delta T, which means change in temperature. So how the temperature is changing for sample 1? How is it changing? From T1, it is changing to T.
So T1, T minus T1.
Wonderful. Which is greater? Which is greater? This is the hotter sample. Now what did we say about T? It would be lying between T1 and T2. Correct? So T1 is less than, T is less than T1.
Yeah.
So change in temperature from T1 it reduced to T.
T1 minus T.
T1 minus T. Now let's look at the second beaker, beaker number 2. Q2 is equals to S, mass is
M2.
M2, delta T is change in temperature.
T minus T2.
Wonderful. T minus T2. Why?
Why? Because the average temperature of T and second beaker is have less temperature.
Yes, correct. Second beaker has a lesser temperature and temperature increased from T2 to T.
Yeah.
And hence it is T minus T2. T is greater than T2. Okay. Now we know that heat lost by sample 1 is equals to heat gained by sample 2. Which means now Q1 is equal to Q2. Correct?
Yeah.
I am gonna erase. Now we have Q1 equal to Q2. Right? So what is Q1? S M1
T1 minus T.
T1 minus T
Yeah.
equal to Q2. Q2 is SM2
T minus T2.
T minus T2. S is the same on the both sides of the equation, so I can cancel it. Yeah?
Yeah.
Now let's expand this equation. I'll multiply M1 with both the terms inside the bracket. M1 T1 minus
M1 T.
M1 T. Wonderful. Equals
M2 T
M2 T
minus
minus
M2 T2.
M2 T2. Right. Now we'll exchange the terms in the equation. We are interested to find out the temperature T. Right? So these terms I'll bring to the one side of the equation and the other terms I'll bring to the other side. Okay? So let's have this same thing and I will bring this from here to here. We have minus M2 T2. If it comes to this side it becomes plus. Plus M2 T2 equals, we have M2 T and minus M1 T from here goes to the other side becomes plus M1 T. Right. Now take T common from these both the terms. Yes, T is common. What is remaining? M1 plus M2 is remaining. Equals, we have M1 T1 plus M2 T2. Okay? We are interested with finding the temperature T. You can send this to the other side. T equals, this is in multiplication here, if it goes to the other side becomes division. M1 T1 plus M2 T2 divided by M1 plus M2. So using this formula we can find out the resultant temperature. When two or more samples with different temperatures and with different masses are mixed, then this would be a resultant temperature. Right? T equals M1 T1 plus M2 T2 divided by M1 plus M2. So right, this is the formula. T equals M1 T1 plus M2 T2 divided by M1 plus M2.
Okay.
Understand?
Yeah.
Now let's revisit those the situations that we have discussed in the beginning of the session. So what was that first situation that we talked about wherein there is no temperature change, right? But just for the sake of our formula, let's revisit that and check if it is working fine or not. There are two beakers of water with 200 ml in each and heated up to 60 degrees Celsius in each of these. Yes? So by logic, we know that when we mix these two, the resultant will also have 60 degrees Celsius. We know this by logic. But let's apply using our formula. What is the formula? T equals, yes, what is it? M1 T1 plus M2 T2 divided by
M1 plus M2.
is 200 ml mass? No, it is volume. Ml, liters, milliliters, these are the units of volumes. No? Here 200 ml is not mass, it is volume. But can we find out mass from this volume given? Of course we can. We know this relationship between density, mass and volume. Density D equals to mass by volume, M by V. Now M equals density into volume. Now the substance in both these beakers is same thing, no? It is water. So density would be same, right? And in this case even volume is also same. So mass would be same, correct?
Okay.
So I don't have to worry about M1 and M2 now because I know that substance is water. Densities would be same and it is same volume, 200, 200. So volume is same. That means mass would be same. So I'll say M1 is equals to M2, which is equals to M. We can do that? Yes? So M, what is the temperature? 60 degrees. So both we have 60 degrees, right? Plus M into 60 divided by M plus M. 60 M plus 60 M. What is it?
120 M.
By M plus N, 2 M. 60 degrees Celsius would be the temperature of the resultant mixture.
Okay.
Okay, so we don't really need the formula to solve this. Let's look at the situation number 3 wherein the masses are different and also the temperatures are different. Remember? What was it? We had 100 ml of water heated to 90 degrees Celsius.
Okay.
And in the second one we had 200 ml heated to 60 degrees Celsius. Correct?
Okay.
Yes. Now here volumes are different. Let's see. Density equals to M by V. M is equals to density into volume. Now M1 of this beaker is equals to density, I am going to be writing it as D, into V1, volume 1 is 100. So M1 is D into 100. Clear?
Yeah.
M2, what would M2 be?
D into 200.
Wonderful. D into 200. Why D is same? Because substance is same. Right?
Yes.
Get it? Okay. Now let us apply this in the formula. M1 into T1. M1 is D into 100. 100 D. Temperature is 90
degrees.
plus M2
200 D.
200 D. Temperature is 60 into 60 by M1 plus M2. 100 D plus 200 D, which is 300 D. Okay? Let's solve this now. You can take D out common and you can cancel it. Correct?
Yeah.
Yeah, we can do that. Right? 100 into 90.
900.
Hun-
9000.
9000. D is common plus 200 into 60. 12,000 divided by 300 D. D and D gets cancelled. Okay? 9,000 plus 12,000 is 21,000 by 300. Zeros are cancelled. 3 ones are 7. 70. So 70 degrees Celsius is the resultant temperature of the mixture. It would exactly be 70 degrees Celsius. That brings us to the principle of method of mixtures, which states that when two or more samples with different temperatures are mixed, then net heat lost by the hot bodies would be equal to the net heat gained by the colder bodies, right? Because when bodies are in thermal contact, heat flows. That is the principle of method of mixtures, and using this principle we have derived the formula to find out the temperature of the mixture when samples are mixed. Get it?
Okay.
Alright. Thank you. Let us meet in the next session to discuss more.